Rutherford's idea of the atom included electrons orbiting at random around the nucleus. And that was acceptable at the time, but then Niels Bohr came along and did some experiments, and his big revolutionary idea was that these orbits aren't happening at random. These electrons aren't just moving around in circles around the nucleus however they feel like. They only exist at very specific energy levels based on what element it is. So the Bohr model of the atom looks a lot like this. You have a nucleus in the middle and then rings around it. These rings represent different orbits or different energy levels that an electron can exist in. An electron only exists on those rings. It doesn't exist in between them. But it can jump from ring to ring. So if you remember from our physics discussion before, if any two pieces of matter collide, there's a transfer of energy of some sort. So we're thinking there's an electron orbiting around the nucleus here, just chilling out at its normal level of energy, and then all of a sudden we shoot an electron going really fast right into it. And some of that energy gets transferred, and that electron gains energy, and it goes up in energy level. We call that an excited electron. It has more energy than it really needs to. Electrons don't like to be excited. They like to be at their very chill state, what we call the ground state, its lowest energy level that it can exist in. So it's going to do all it can to get down there. In order to get back down, it has to release energy. The energy that an electron releases to go down an energy level is a photon. Those photons are actually just particles of light. And if you remember from our lesson on waves, waves have different wavelengths and frequencies. And when you relate it to light, it has to do a lot with the energy too. So how much energy is given off affects the frequency of that photon wave. And then it also then reflects the wavelength, or affects the wavelength, which changes the color of the light. So Niels Bohr did some experiments with gas discharge tubes, which really just means you put a gas inside of a glass tube and you shoot electricity through it. And that's what this simulation is here. So we have some electricity here, and we're going to shoot electrons off of this panel, and it's going to go in through this vacuum tube of hydrogen gas and hit the hydrogen atom. And you'll see over here on our energy diagram, this little electron, he's going to go up energy levels and then fall back down. There'll be some squiggly lines that show you when he moves. And then you'll see a little photon pop off of the atom. So let's go ahead and throw some electrons at it. You can see that electron over here in the hydrogen atom just going up and down energy levels. You can see these colored bits of light flying off. Let's put it in slow motion so you can see it a little better. So you've got some purple light coming off there, some ultraviolet, some more purple. And down here on our spectrometer, it starts to count up all of the photons that get shot off of this. And you'll notice the longer we let this run, we only get certain bands of light through here. So we've got some ultraviolet, some infrared, but with our visible light, we have a very distinct wavelength of purple light, very distinct wavelength of blue light, and then some light blue light here too. And that's it. There's no other photons that get released just because of the nature of the hydrogen atom and the energy levels that the electrons are allowed to exist in. If we did this with more atoms, we could see, let's take it back to hydrogen here. If we do that with more atoms, we can see those wavelengths, those wavelengths of light here on the spectrometer. And that's like the fingerprint of this particular element. We can look at different elements too, maybe sodium. You can see it's got this orange band and this yellow band, and that's about it as far as our visible light spectrum goes. If we did neon, you would see a red and some yellow, a little bit of green, but mostly red, orange, and yellow. So those represent real gases. And if you excite them, now this is where we get our neon lights. Those are just gases inside a tube, and different mixtures of gases will give you different colors of lights. But if we look at just a simple element in a gas discharge tube, and we look at it through a diffraction grating, it shows the whole spectrum of light coming off from that. And if we look at the sun, we see the whole rainbow. That's how rainbows work. It's the whole spectrum of visible light. But if we look at just one certain element, we only see certain bits. And that, again, is because of those different levels of energy that electrons can exist at.